If you have time series data and you consider estimating a linear regression model, then one of the issues that you need to consider is the issue of autocorrelation. We know that if you have autocorrelation and you consider a simple static time series model, then the OLS estimator is still unbiased and consistent, no longer efficient, but the standard errors are inconsistent. So therefore, it's important to actually try to figure out if autocorrelation is an issue in your data. This lecture is about a very simple test for autocorrelation called sometimes the Breusch-Godfrey test. So in this lecture, we will only consider the Breusch-Godfrey test in a fairly simple model, namely a linear regression model, which is static. No lagged x variables and no lagged y variables. We will assume that all data is stationary, and we will assume that the explanatory variables are exogenous. The exogeneity assumption is important in this lecture, and that's why we do not consider cases where we have lag dependent variables, for example. So next we will make a very specific assumption about the error terms. We will assume that the error terms follow an AR1 process. The AR1 process is an extremely useful assumption for considering autocorrelation because it has both cases as special cases. You can have autocorrelation and you can have a case where you have no autocorrelation. The AR1 process, remember, says that the error term today, epsilon t, depends on the error term in the previous period with the row in front of it, plus a new error term that we call nu t. I specifically note that it's the error term that we assume follows the AR1 process in this model. It is not the dependent variable y. The y variable is only determined by the x variables and not by its lagged value. The AR1 process for the error terms is assumed to be stationary, so the row parameter must be between -1 and 1, not including -1 and 1. We also assume that the second error term, nu t, is white noise. White noise, remember, just meant that it has expected value 0 and there is no correlation between the nu t's. Now, I also want to point out that in this AR1 process, it's different from what we've seen before because everything in that process is unobserved. We don't observe epsilon t, we don't observe epsilon t minus 1, rho is an unknown parameter, and nu t is an unknown random variable. But as we will see in a second, even so, this specification turns out to be very useful. So if we look at this AR1 process for the error terms, two things are worth noticing. First, there is no intercept in this AR1 process. And the reason for that is that we need the expected value of the error term to be 0. And that's why we have no intercept in the AR1 process. Second, if rho is exactly equal to 0 in this AR1 process, then it says that epsilon t is nu t. But that simply means that when rho is 0, epsilon t is white noise. With white noise, we have no autocorrelation. So rho equal to 0 corresponds to the case of no autocorrelation. We know from the AR1 process that when you increase rho from 0, that will increase the covariance between epsilon t and epsilon t minus 1, thus making the autocovariance problem more severe. So the bigger the rho in the AR1 process, the worse is the autocorrelation problem. With a rho close to 1, there are long cycles in this error term. So the shock to yt today will be pretty similar to the shock that will affect y in the next period. So the focus of this lecture is on autocorrelation. And we have now just concluded that we have a model where autocorrelation is present when rho is different from 0, and we have no autocorrelation when rho is not 0. So if I want to set up my null hypothesis, which is there is no problem in the model, that is, we have no autocorrelation, then the null hypothesis should be rho is equal to 0. This is precisely the null hypothesis that I want to test. Again, if rho is 0, epsilon t is white noise, and we have no autocorrelation problem. If rho is different from 0, then there is a correlation between epsilon t and epsilon t minus 1, and we have autocorrelation. So the next question is then, how do we test this hypothesis? Because I don't have data on epsilon t. If epsilon t data was available, I could actually run this regression that represents the AR1 process and estimate rho, but I can't do that since the error terms are unknown. Well, fortunately, the error term can be approximated using the residuals. And we are actually in a little bit of luck here, because even if we have autocorrelation, so even if rho is different from 0, I know that the OLS estimation of the linear regression model will give me consistent and unbiased estimates of beta. So that will guarantee that the residuals will have no bias in terms of approximating the error terms. So based on this argument, here is the procedure for testing for autocorrelation. So you just begin by estimating the linear regression model using OLS. So you get estimates of all the betas, we call those B, but remember that also gives you all the OLS residuals. So save those, save all the OLS residuals. We call them E1 through ET. Remember that the goal is to estimate rho and to figure out if that is significantly different from 0, where rho is the parameter in this AR1 process. Alright, so we don't know epsilon, we've done the OLS regression, so we have residuals. So if I replace epsilon t with et, it says et equal to rho et minus 1 plus nu t. And I have a regression that I can actually run. We call such a regression an auxiliary regression, as it helps us to estimate an important parameter of the model. Now it turns out that the estimation of rho will actually be improved if you add all the explanatory variables that you have in the original regression to this auxiliary regression. So the auxiliary regression that we estimate will actually be the following: et on rho et minus 1, and to that we add everything from the linear regression model: beta 1 plus beta 2, x2 plus beta 3, x3, and so on, all the way until the final x variable. So we estimate this model, get estimates for rho and all the beta parameters. In this case, we don't at all care about the estimates of the beta parameters. All we care about is the estimate of the rho parameter. So the important variable in this case is the lagged residuals et minus 1. From this regression, I can simply test the null hypothesis that rho is equal to 0. We can test this with a simple t-test. Due to the fact that we have a lag-dependent variable, the test is only asymptotically correct. So the t-value in this case will be approximately standard normal as long as S is fairly large. So let's have a look at how to do the Breusch-Godfrey test in eViews. Here I have some data on the help wanted index, an index for the number of help wanted ads in newspapers, and the explanatory variable is UN, which is unemployment. Monthly data from 1951. So I want to test if we have autocorrelation in the model where HWI is explained by UN, a simple static model. First step, you estimate the equation just using OLS. So HWICUN. Now, I'm not at all claiming that this is a realistic model since it's static. We will simply use it to illustrate how to test for autocorrelation. So once you've done this, the residuals are saved in this resid vector. So in the second step, you can actually perform the auxiliary regression yourself by just running a second regression. However, due to the popularity of the Breusch-Godfrey test, this procedure has already been programmed into eViews and most econometrics packages. So all you have to do is go to View, Residual Diagnostics, Serial Correlation LM Test. That's the Breusch-Godfrey. The lags to include, well, the number that you're supposed to specify here is the number of lagged residuals that you include in your auxiliary regression. We only include one lagged variable, so we need to set that to 1. I set this to 1, OK, and I get the result for the auxiliary regression. As you can see, the dependent variable will be resid, the residuals. The explanatory variables are resid minus 1, lagged residuals, my x variable, and my constant. This is the estimate of rho. These parameters are completely non-interesting. We've just included un in order to come up with a slightly better estimator of rho. If I want to test if this is significantly different from 0, I go to the t-statistic. We have a large number of observations, so the test statistic will be approximately standard normal under the null, and we have a p-value which is basically 0, and that means that we should reject the null hypothesis that there is no autocorrelation at pretty much all levels of significance. So in this model, we need to conclude that the error terms are autocorrelated. The procedure in Gretel is extremely similar. Just go to Model, Ordinary Least Squares, estimate HWI using unemployment, click OK. Then to do the Breusch-Godfrey test, unless you want to do it manually, you can go to Test and Autocorrelation. Set the lag order, set it to 1, and you have the same result here, where the p-value of interest is right there. Remember that the t-test is equivalent to an f-test, where the first degree of freedom is 1. So instead of looking at this p-value, you can also look at this p-value. The f-value right here is simply the square of this t-value. But the p-value that you find here and here will be the same. Gretel also presents two alternative tests for this hypothesis, but all of these tests are asymptotically equivalent. As long as n is large, they will give you approximately the same result. Another older test for autocorrelation is the Durbin-Watson test, and the Durbin-Watson statistic is also typically presented in most packages. If you look at this statistic, and you look up the Durbin-Watson critical values, you also get the result that the error terms are autocorrelated. Now, both of these econometrics packages suggest the possibility of having more than one lag of the residuals in the auxiliary regression. So let's just have a quick look at this possibility. So an extension to this Breusch-Godfrey test, where we had one lag on the error terms, that is, we model it as an AR1, is to model the error terms as an ARP process. Remember, the AR2 process, if I want to model my error terms as an AR2 process, I write epsilon t is rho epsilon t minus 1 plus, now I need one more parameter and epsilon t minus 2. So in that, to accomplish that, I add a 1 to this one, so I can do a 2 on this one. I get two rho parameters. and then plus an error term. If we do the same thing, we estimate the model using using OLS and get the residuals, then I can replace that with ET, that with ET minus 1, that with ET minus 2. To get my auxiliary regression, row 1, let's put it in the correct position, plus row 2 plus new t. To improve the estimates, and we can do that because we are not using the actual error terms but the residuals, we also add the explanatory variables. So let's say we just have 1 to make it simple, xt plus new t. So this will be our auxiliary regression. In this case, remember that no autocorrelation means that there is no correlation between ET, well actually epsilon t, there is no correlation between epsilon t and any of the lags. So no autocorrelation must imply that this one must be 0 and this one must be 0. So the null hypothesis in this case for the AR2 is that row 1 is 0 and row 2 should be 0. We don't need to say anything about the beta parameters because the x variable is just a helper here to improve the estimates. So in the general setting, in an ARP process, the auxiliary regression would look, the ARP process looks like this. Epsilon t depends on epsilon t minus 1 and lags all the way to epsilon t minus p. To do the auxiliary regression, replace all the epsilon with e and add all the explanatory variables. So it will look like this. We estimate this, and the null hypothesis is that all the row parameters must be 0. We can test this not with a t-test because we actually have p restrictions now, but with an f-test or the LM test. Both are typically presented in econometrics packages, and again, they're asymptotically equivalent. Large enough n and they will give you the same result. For example, to do this in eViews, you would just go View, Residual Diagnostic, Zero Correlation LM Test, set the lag to 2, and you can see that in this case it has added 1 lag on the residuals and 2 lags on the residuals. In this case, we cannot look at these p-values. We cannot just do a t-test, we need to do the f-test or the LM test. So the f-test is specified up here in the first row. That's the null hypothesis that both of these are 0. That's the f statistic and the p-value. Or you can do the LM test nr square and look at the chi-square distribution. In both cases you get the p-value of 0, so again you would reject the null hypothesis of no autocorrelation. And in Gretel you would do the same, just test autocorrelation, set the lag order to 2, that will give you the same result, and you can use any of these 3 asymptotically equivalent test statistics.